Hello. So this is a practice talk for SAC next week. And in this talk, I will go through with you how a countermeasure that is meant to be secure against fault attacks fell short of its promise. And this work is in collaboration with Svetla and Vansi. And in this work, we first break the RS-mask countermeasure, and then we propose a fix on it. So let's first start with some background on physical attacks. Cryptographic algorithms are designed to be secure against cryptanalytic attacks, but their implementations are still prone to physical attacks. The first group is the passive attacks, and this is actually the well-known side channel analysis, in which the adversary is actually exploiting the observable leakage coming from the physical effects in the hardware device. For example, they can exploit the data-dependent power consumption. Masking is the most widely used countermeasure against side channel analysis, in which the secret data is split into a number of shares, and each share is statistically independent of the secret data. So if we observe all but one share, then we have no information regarding the secret data. Besides the theoretical analysis of masking schemes, we also have a practical evaluation and side channel analysis, and it's called TVLA, in which we put the implementations on a hardware device, and we check their behavior in the real world, and we check the security of them in practice. Unlike side channel analysis, the active kind of attacks, which is the fault attacks, they intentionally disturb the computations using some physical means. For example, they can play with the clock and voltage of the circuit, and they can induce some glitches. Against this, the most widely used countermeasure is combining redundancy and masking. So in this way, we also protect against side channel analysis. If we consider the simplest case, what we can do with redundancy is that we can do error correction. So this means we always get the correct output. So it feels like there's no fault injection at all. Or we can do like error check of all the critical values. So we can detect all the injected faults even before they get ineffective. So it also means that they would be data independent. Or we can just ensure the fault propagation. So each injected fault would go to the output. So we can detect all the injected faults. And this would also make it independent of the secret data. Or another alternative is using random space masking and performing the operations on that random space, and which the RS-mask countermeasure is doing actually. And also different from side channel analysis, in fault attacks, we don't have any practical evaluation framework. The analysis is mostly done in theory or tool-based, but these available tools are only evaluating the security of smaller circuits, which means we can't really evaluate a whole protected AES circuit. And this led some overlooked vulnerabilities. For example, kappa, which inherits security from an MPC protocol. It was broken because it didn't have solid security evaluation. And the very first gadgets that is based on combined non-interference, they had theoretical analysis, and they also had tool verification, but they were broken again. And RS-mask, which also doesn't have a solid evaluation, so it's also broken in this work. And now let's go through the RS-mask countermeasure. And the goal in this countermeasure is to maintain uniformity even when a fault is injected. So this means even if we inject a fault, it's not going to induce any bias, so the adversary cannot exploit it. The core idea is to map the variables to a random space and do the computations in that random space and transform the output back to the original space. And in this way, the computations are going to be independent of the secret data. And they apply this idea to AES, and then they issue first-order SCA and first-order fault security. So in this idea, it's really easy to protect linear operations because masking is actually working as a random space mapping, since each share is already uniform. And in this setting, if we fault all but one share, then we can't really induce a bias to the unshared data, because the unfaulted additional share is going to be uniform, and when we XOR it to the other shares, then the result is going to be uniform as well. But it doesn't work with S-bugs, because in an S-bug structure, we have non-bijective components. So this means even a single fault can induce a bias at the output. So this means we need to derive a different random mapping for the S-bugs. And in the paper, they propose to use this structure such that we have an epsilon mapping, and we map the inputs such that the output of the mapping is the output of the S-box plus a random uniform value. And in this way, even if the output of the mapping is biased, the correct recovered value is going to be still uniform because R is a uniform value. And so now let's see how the authors derived the random mapping for the S-box inversion. So they based on the can-write construction, and they derive the equations for the inversion. And they do it separately for the zero input and non-zero input because in the field, the inversion works differently for the zero input. It's directly mapped to the zero output. First, let's see the non-zero input. So what we want to do is the output plus a random value. First, let's see how we derive the actual output. So as you see it from the circuit, the actual output is actually computed by multiplication of the input and the Y inverse. So this is easy. And how we can derive random is, if we know that the input is non-zero, this means Y and Y inverse are going to be non-zero as well. And if they are non-zero, then the multiplication of Y and Y inverse is going to be 1. So we can just use this information and add this value to the output. And this is actually what we wanted from the mapping. So we can just write it like this, just to reduce the number of multiplications. So everything is okay, but what if Y is faulty? Then we are not going to get the effect we want, because Y inverse is going to be faulty as well, since it's based on the faulty Y. And this will cause the output to be biased, so the mapping is not going to work. What we can do is, we can use a separate data pad to compute Y. So we just take the input, and with a separate circuit, we compute Y. So if this Y is faulty, then Y inverse is not going to be faulty. Or if Y inverse is faulty, then this Y is not going to be faulty. So we know what to do for non-zero input, and let's see what we can do for zero input. If the input is 0, then it means Y is 0, and Y inverse is also 0. So the previous mapping is not going to hold, because Y inverse times R is not going to be equal to R. Now what we can do is still we need the same mapping. This mapping actually means that the output should be 0 plus R, which is actually the inverse of R inverse. So here what we can do is, we can just add the inverse of R to the input only when X is 0, then we would get the desired output. And now we had the mapping for zero input and the non-zero input, and let's see how we can just unify them in a single circuit. We can just define an auxiliary variable, which takes the value of 15, and this is the unity in the field, and we compute it with a Kronecker delta function. And when f is 15, then we add the inverse to the input. And when f is not 15, when it's 0, then we compute the additional circuit that you see in red here. So we compute the additional circuit that we saw in the previous slides. And when the input is 0, we don't compute it, and we just add the random to the input. And now let's see how the authors analyze the security of this countermeasure. First, the security for statistical fault attacks is coming from the theorem that the mutual information between X plus R and X is 0, if and only if R is uniformly distributed. So this means, we can't really do any statistical attack on the output. For the security against differential fault attacks, they actually have an infection circuit built into the AES inversion circuit. And here we already have X, the input to the inversion, and we also already calculated Y inverse. So now what we can do is we can just get the multiplication and compute the actual inversion. And if there is no fault injected to the circuit, then this plus the random should be equal to the output of the random mapping. And if they are not equal to each other, then we can just use this differential and randomize it and use it to infect the output. So in this way, the output is going to be random, so they can't really use it for differential attacks. So this was their security analysis of the countermeasure. And now let's see how we analyze the security of the countermeasure. First, it's not security related, but it brings additional overhead, that they compute the inversion circuit order on the random with the added register layers. And the authors claim that they do it so that it would be secure against glitches, but R is just a single share, and under probing model we can already probe it and we can just see what it is. So this just brings additional overhead. And besides this, we identified 4 areas for the fault injection that an adversary can do CIFA or DFA. For the time constraints, I will only tell you about 2, but in the paper you can see all the fault locations with all the details. The first one is getting the input somehow faulty. We can either fault the input to the whole circuit, or we can just fault the XOR operation where we recover the actual input to the inversion. So when we fault one of these 2, then the input we get is X plus delta. But as you saw in the previous slides, the infection mechanism is using the same input to compute the differential between 2 outputs. So it's not going to detect the output, so an adversary can just do a differential attack on that. And the second location is any component in the additional circuit inside the inversion. So if we fault any of the red components, then this means the input to the multiplication with F is going to be faulty. So we know that F is 0 when the input is 0. And if a multiplication input is 0, then this means the fault is not going to propagate to the output. 0 is going to cancel it. If X is non-zero, then we know that F was 1, so the fault is going to propagate to the output. So what an adversary can do is they can just repeat the computation once more without the fault injection. And if the outputs are same, then this means the input was 0 because the fault didn't propagate to the output. And in the analysis of the authors, so they do TVLA for the side channel analysis, and this shows the security of the scheme. And for the fault, first they check the distribution of the faulty and correct S-box outputs, and they also do a CIFA simulation using a software. But what they do is they do both analysis using only a single fault location, and they say that the whole scheme is secure, but it's not that correct without checking all the components in the circuit, because they missed something, so we found the vulnerabilities. And as response to this vulnerabilities, we proposed a fix. So we proposed an AES-specific countermeasure. For the adversary models, we first assume the glitch-extended robust deprobing model for the side channel analysis. And for faults, we assume gate register faulting model, in which an adversary can inject a fault to a threshold number of gates or registers in the circuit. And for the security model, we slightly change the correctness, and now we allow the adversary to receive a faulty output, but we will make sure that this output is non-exploitable. The previous definition stays same, and the probability of the abort signal is independent of the secrets of the circuit. And now the goal in this countermeasure is to derive a uniform mapping for all inputs. So we are not going to have different mappings for 0 and non-zero inputs. First, let's look at this table that is derived from the values appear in the S-box inversion. And the important part is that if we take these 2 values, it's always 1, and independent of the value of the X. And we have the next 2 expressions where the input times YY inverse plus 1 is 0. So we're going to use these 3 expressions in the derived mapping. And let's see how we can use them. So I put that in the corner so that we can keep it in mind. First, the mapping we want to derive is output plus R. First, we compute the output, and this is just same with the previous one. It's X times Y inverse. Now we need to add the random. Now how we can do is, if you remember the multiplication of these 2 values, and the multiplication output is 1, independent of the data. There is also R, but I fixed it in the morning, so it disappeared. So this times R, I will fix it. And now how we can write this is, we can just add this term to X and then reduce the number of multiplications. So it's similar to the previous countermeasure. And it doesn't change the correctness with the additional terms, because we know that X times YY inverse plus 1 was 0, so we didn't change the correctness of the expression. Of course, just like the Arias-Mas countermeasure, we have some exploitable output differences, and how we hide them is we add this term to the output. So this is always 0 independent of the secret. But if there is a fault injected in the circuit, then this evaluates to a random value. So this means we just add a random value to the output, so it's not exploitable anymore. But if you remember the can-write construction, we have one more inversion inside. In the RS-mask countermeasure, they didn't have anything for that, but in this countermeasure, we just derive the same equations for the inner inversion, and we just make it complete. And now we figured out how we can protect against statistical attacks and also differential attacks, but when the fault is injected somewhere in the middle. But what happens if we inject a fault to the S-box input, because we exploited it in the RS mask? To protect against this, we just duplicate the input, and we compute the additional circuit on the new input. So all the red components you see here are coming from the expressions we derived in the previous slide. Yeah. And some hardware implementation details about the countermeasure is that it's over 3 shares, and the implementation is based on consolidating masking schemes. So we issue second-order SCA and first-order fault protection. And how we assess the security is we have a TVLA evaluation for the second-order SCA. And for the fault evaluation, we were not able to use provable methods because the whole design is quite large and we are not based on the security notions that those tools are based on. And instead, we analyzed the detection rate for all inputs, but this time we simulated faults on all the components of the circuit. And for the differential attacks, we analyzed the distribution of the output differences, again for all inputs and for all fault values. And what we saw was they were uniform and they were not exploitable. So in this work, we identified several vulnerabilities in RS-mask. And this was due to insufficient formal proof and evaluations. So they had some overlooked details. And this leads us to the conclusion that we need more solid fault evaluation frameworks in this field so that we can test the implementations in practice. And this is the biggest challenge. And after this, we just propose an AES-specific countermeasure with a uniform mapping based on the idea of RS-mask. And this is the paper link, if you would like to check.